Hey guys, Majovi, and welcome to the second video in our Let's Learn Java series. And today I'm going to be explaining multiplication, division, subtraction, addition, mathematics. We're getting math now. So we've learned how to print out stuff. Now, how do we do math? Okay, so we're not going to print out a string of characters. We're going to print out the math, okay? So in order to do that with our print line is very flexible. If we type in 5, right? Get rid of these comments. Don't really need them. If we type in 5, save it. Oh, where did my wheels? And we compile it. And we run it. It prints out the number 5, right? We don't have to do anything special. It will print out 5. Good. Can I change the font in this? Pretty sure you can. Yes, you can. Ha 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 ha. Boom. That looks nicer, doesn't it? All right. 5. So now when we run it, it says 5. That's easier for you guys to read. Okay. So we can do math, right? You can do math that you think you can do. Go 5 plus 5. Wow. Okay. Let's save that. Compile it. Give the old run. 10. Boom. Very simple, right? You can do subtraction, which is the same, but it minus. Multiplication is star, right? So on your numpad, there's a star. Is that on your main keyboard? Yeah, it's under 8. Under the number 8. And you have division, which is slash. Alright, now you also have a couple odd ones. And there's some tricks to this that you may not see at first. I'm going to have to explain it to you anyways. There's also a thing called mod. What mod is, it gives you the remainder. And there's also bit shift operations, which is very advanced. But I'm going to explain 2 of them to you today because they are pretty simple and it's math related, which is bit shift to the left and bit shift to the right, which is written like that. All right, let's get a nice little string of math going on here, right? We're going to print all these out. Let's get a bunch of print lines. We're going to have all the examples on screen. That sounds good to me. Tab those over. Okay. We'll have 5 plus 5. Right. Let's make it a different number. We'll do 5 and 9. Because those are weird numbers. We'll do 5 minus 9. 5 times 9. 5 divided by 9. 5 mod 9. We're not doing 5-bit shift 9. It'll be, I mean, we could. But we're going to hold off. We're going to hold off because I need to explain that more before we actually do the bit shift operation. Okay. So, what should we expect? It'll say 5, right? It'll say 14, do a slash. It'll say 14 here. We'll get a -4. 9 times, we'll get 45. Now, 5 divided by 9 will give us a decimal, which actually it should be 0.5 repeating if you know your divisions by 9. And 5 mod 9, which is 5 divided by 9 plus the remainder, which it doesn't go into it. It should give us 5. Mod's a little weird. I don't use it that often, but I think the result should be 5. Okay. Now let's I have no good place to put this. We'll compile it. Everything compiles, and we'll run it. Yeah. I was right with the mod. Okay, but we have a problem. Do you see the problem here? All right, let's line these back up with what we predicted. All right, we printed out 5 to start with. 14, correct. -4, correct. 45, correct. 5 divided by 9, we should get 0.5. Oh, why is it 0? 5 divided by 9 is not 0, and 5 mod 9 is 5. I was correct. But 5 divided 5 point, that's not right. That should be a decimal. Why is it not a decimal? Okay, Now we've run into the problem that most people run into, and is a problem that a lot of people cause, and they're not aware of it, because, I mean, sometimes it's hard to see it. But there's there's two different types of numbers in programming. You have integers, which do not have decimal places, and you have floating point numbers, which have which has a decimal place, right? So this 5 divided by 9, that is an integer divided by an integer. You get an integer result, okay? So you get 5, that's just an integer. 5 plus 5, 5 plus 9, those are two integers. You get an integer result. We want a decimal result. We want to have a decimal place, because that's stored entirely differently than an integer. So how can we say, no, we want a floating point result? The way to get a floating point result is one of the numbers in the operation has to be a floating point number. They can both be a floating point number, but at least one needs to be a floating point number. How can we do that? There's a couple ways you can do that. The easiest is to say 0.0. Is to say 0.0, right? We can say 0.9, 0.0, right? We want to have a decimal like this. Another way is to write f after the number. Okay? Now it's going to print them off a little differently now that we made these floating point numbers. So you can either do the 0.0 and the f, and there is a difference. Now the 0.0, Java will interpret that as a 64-bit floating point integer, number, and the f will interpret it as a 32-bit floating point number. The difference is how much data there is. Now, in Java, these have terms. A 64-bit floating point number is called a double, and a floating point number that's 32 bits is called a float. So these are doubles, these are floats. Okay? Now, if I run this, we'll get the same result, right? We should get the same result. Although, because it's printing out a floating point number, it should tack on a 0.0. Now we run. Now you see how it tacked on a 0.0 there? Well, that's just what it does. So we get our 5, and it adds, because we're printing out floating point numbers, it just throws a 0.0 on there, because it does have a decimal place, and a decimal place is 0. 14 is 0, 14.0, negative 4.0, 45.0, and there's our 5 divided by 9, or 0.5 repeating. Now, floating point numbers are only accurate up to a certain point. Now, since we made it a double, look at all these 5s we got. Now, that's because it's 64 bits. 32-bit one has less information. So if instead I made these 5f divided by 5,9, notice something. It's going to have less 0. It's going to have less, right? I'm going to copy that because I want to try and save this, right? So this is our first result, right? I'm going to close this out. Oop, no, I want to go back. Compile. Run. Whoa, what happened to all our 5s? Our 5s have all disappeared. That's because we're using floats instead of doubles. And floats are less data. 32 bits versus 64 bits. That's a lot less data. So if you really want accurate results, you want to use doubles, which is the 0.0, and floats if you're concerned about memory, which typically you're not. So typically you just use a double. So just add a 0.0 after your number, you'll be fine, right? So now let's look at this mod a little bit more, since we've gone over our floating point problem. So we fixed that. We're just gonna make them all. Let's get rid of these comments. Let's get rid of all this, because I'm gonna focus in on this. We don't need mod. So if we said 5 mod 9, 5 mod 5, what is that? Really? Okay. I'm gonna compile this, and then I'm gonna run. We get 0. 5 mod 5. 5 divided by 5, you get a remainder of 0. Okay. Now if we did 5 mod 6, right? You get 5 divided by 6, you get a remainder 1, right? That's what I wanted. You get a remainder of 5. It goes from one side to the other. So 6 mod 5. If you take 6 divided by 5, you're left with 1 out front. Which gives you 1. Works, right? Perfect. The main use of this is determining if a number is odd or even. Because you can mod a number. So say we have 5. If we mod it by 2, it'll give us a 1 or a 0 if it's even or odd. So we get 1 because 5 is odd. But if we make it 6, you get 0 because it's even. That's one of the main uses you use for it. Another thing to note is that the Java does not take care of, it does do a bit of MDOS, as in it does things in the right order. So 5 plus 6 times 4 will give you a result of, actually let's do 25. So it'll give you a result of 25. Which is exactly what it gives you, instead of giving you 40, right? It does do MDOS. But you can use parentheses as well to make sure that specific actions are done before other actions. Right? Now, if I wanted it to be 40, put a parentheses around the 5 plus 5, it'll do that first, and then do the multiply by 4. So we get 40. Very simple. Alright. Now, as I promised, I'm going to get into the bit shift operating, which is advanced. So don't worry if it seems a little advanced. It is. You don't use it very often. There's only like one use of it that I want to show you. So now let's look at binary. Okay, so this is going to be like really small. So say I'm not counting these out. Say that's 1. I didn't count out the zeros. Say we have 31 zeros and 1 1, right? That is literally the number 1, right? Now I want to bit shift 1 to the left by 1. What do you think the result will be? Right? I'm going to shift this bit over to here. That should give us 2, right? So we compile it. Oh, that's a comment. That is a comment. We're gonna compile it again, and then we're gonna run it. We get 2. Oh, look at that, right? Because I moved this 1, right, from this location to this location. I shifted it over by 1 spot. Now, if I shift it over by 2 spots, that takes this 1 from here to here, right? And that gives us 4, right? Wow, look at that, 4. Because just remember, binary it goes 1, 2, 4, 8, 16, 32, 64, 128, all the way on all powers of 2. So say we had like a number 12 and we wanted to square root it. This kind of works. You can get a rough square of it just by shifting it over by 1. So if we save it, or I think it might be switched over by 2, but we're going to save that. We're going to run it, and we get 56. So we divided it by 2. Actually, yeah, we divided by 2 by shifting it by 1. We can divide it by 2 again. If we shift it by 2, we get 28. Wow, crazy, right? And I'm pretty sure this gives you a square root. Otherwise, there might be a little mistake in here. One thing to note, though, about bit shifting is this only works on integers, and it will give you an integer result. There is no way to give it a floating point result, because floating point numbers are inherently different. At the algorithm level, like at the storage level, compile this, we run it. Oh, there's a way to get this to give you like a square of it, square. But anyways, I think if you shift it to the left, though, you just double it. You can square it. You can multiply it by 2, square it up. You know, it's kind of a handy thing to do. There's very selective case usage for it, right? Of shifting up your bits and all that. Yeah, don't get the squares. I'm mistaken of something else. But anyways, by moving the bits around, you can get different results. So like 120, that would be like 102. So we got 2, we got 10, not 2, 1. I get 10 here. So 1, 2, 12, 8. You got to add these together. So you got 2, 4, 8. We're at 12, and then 100. Whatever. Going off topic. Don't want to go too far off topic here. So, anyways, you can move bits around in memory by bit shifting it over and around and up and down, left and right. One of the main uses, though, is color data. So, like, you store color data. Have you ever seen like numbers like this, right? This is hexadecimal, which means these go from 0 to F. And so this is your alpha color, your red color, your blue color, and your green color. And this is all stored as one integer. You can parse out individual information by shifting the bits over and reading the bits, which require two other actual bit shift operations, but those are also more advanced, and we'll be into that later on. But for now, just know you can move bits around in memory like that. So I think that's going to do it for this episode. Comment, rate, subscribe, and thanks for watching.